Go outside tonight, if the sky happens to be clear, and give your eyes a little time. Not a glance. 20 minutes with no phone and no porch light. Nothing bright anywhere in your field of view. And the sky will slowly hand you far more than you expected to be up there. The first few points arrive almost at once. Then more. And after a while, the dark between them fills in with fainter and fainter specks, until the whole bowl above you looks crowded and busy and packed from one horizon to the other. That feeling is real, and it is worth sitting with for a moment. You are not imagining it. People have stood exactly where you are standing, and felt this for as long as there have been people to stand anywhere. The sky looks full. It looks permanent as well, which is most of the comfort, because the same points come back in the same arrangements season after season, and your grandparents saw them in those arrangements, and so did everyone who came before them. Let us start with what your eyes are actually collecting. On a very good night, well away from any town, with your vision fully adapted and the moon below the horizon, you can pick out close to 2,500 separate stars. Perhaps 3,000 if your eyes are young. Add the half of the sky hidden under your feet, and the whole naked eye inventory, north and south together, comes to roughly 9,000 points of light. That is the entire catalog, 9,000 in total. Every person who looked up before the telescope was working from that same short list, and so is every person tonight who steps outside without one. Most people never get near that number. From an ordinary suburban garden, the count drops to a couple of hundred, and from the middle of a city, you might manage 20 or 30. The stars are still there. Your eyes are looking through a lit fog of our own making, and by most estimates, something like 80% of people now live under a sky like that, and a great many of them have never once seen the band of the galaxy. That is a recent thing, and one of the very few problems of this size that simply switches off. The limit of a human eye is a matter of brightness, and it sits at about magnitude 6 on the old scale, a scale that runs backwards, with the bigger numbers meaning fainter light. Each step down is roughly 2, 5 times less light. Lift a pair of binoculars and the count multiplies several times over, and a small telescope reaches stars millions of times fainter than anything you can make out standing there in the dark. The eye is not a bad instrument, only a small one, and every one of the points on that short list is a neighbor. Not a single star in the naked eye catalog sits outside our own galaxy. Sirius, the brightest star in the night sky, is 6 light years away, which sounds like a great deal, and by the standards of a galaxy is nothing whatsoever. Vega is 25 light years out, and Arcturus is 37. Most of what you can pick out unaided lies within a few hundred light years of your back garden, and even the rare exceptions sit inside a few thousand. Our galaxy is about 100,000 light years across. Your entire visible sky is a small bubble a few hundred light years wide, sitting inside a disk 1,000 times wider than the bubble, and it is an easy and very old mistake to take that little room for the whole of things. The list is also a strange sample, chosen for you by brightness rather than by distance. Your eyes select the loud ones. Proxima Centauri is the nearest star to the Sun, and no eye has ever seen it unaided, because it gives out barely 1,000th of the light the Sun gives. Of the 100 nearest stars, you can see perhaps 10. The other 90 are up there in the same sky, in the same directions, at closer range than almost every star you know by name, and they are simply too dim to register. Most of the galaxy is made of stars like that, And the ordinary star is not a bright white lamp, but a small red ember that would be invisible from a few light years away. So the sky you know is a sky of exceptions. Our own star belongs on somebody else's list. Seen from Sirius, the sun would be a plain yellow point, easy enough to notice and in no way remarkable, sitting in a pattern that has no name because nobody there has named it. There is another thing worth knowing about that view before we leave it. The sky is flat to your eye. It has to be, because human vision cannot judge depth past a few tens of meters. So every point gets pressed onto the same imaginary dome at the same imaginary distance, and the pattern you see is a pattern of directions and nothing else. The stars of a constellation are not together. Take the three in the belt of Orion, evenly spaced, obviously a set. Two of them sit at something like 200 light years, and the third is several hundred light years further still. They are not a row. They are three separate things at three separate depths that happen to line up from this one address, and from a star off to the side, the belt would not exist. The distances there are not settled, by the way. Those numbers have shifted more than once as the surveys improved, and we know the direction of a star far better than we know how far along that direction it sits. And the permanence is honest enough on our own timescale. Those arrangements have held through every written record we have, and the constellations named in Mesopotamia 4,000 years ago are still recognizable from the same latitudes tonight. Stretch it further and it comes apart, because every one of those stars is moving at tens of kilometers a second, and in 100,000 years, the familiar shapes will have slid into other shapes that nobody has a name for yet. That sliding is very slow, overspans far longer than any record anyone keeps, which is exactly why the patterns have looked fixed for as long as people have been writing them down. There is one more quiet thing in that view. You are not seeing a single moment. The light from Sirius left in the middle of the last decade, and the light from Betelgeuse left before you were born, and the light from the faint giants inside the band left before there were cities on this planet. The sky is a mixture of times. It always has been, and nothing can be done about it. And it means the night above you is less a photograph than a very long letter that happens to arrive all at once. Now, if you can get far enough from the streetlights, your eyes can do one more thing. A soft band appears. It runs right across the sky, wide and uneven and a little warm in color, brighter along some stretches and torn by dark lanes in others. It is not cloud, and it is not weather. That band is the reason our galaxy carries the name it does, because for thousands of years it looked to people like something spilled. Galileo pointed a small telescope at that band in 1610. The band came apart into individual stars. He described countless stars, more of them than he could number, and that was the first solid evidence that the sky had depth, and that the faintness of a thing might be a fact about its distance rather than about its size. Almost everything on the naked eye list is inside our own galaxy, and there are a few honest exceptions. On a very dark autumn night in the right direction, there is a faint oval smudge you can just about hold at the corner of your eye. That is Andromeda. It is a galaxy in its own right, and the light landing in your eye from it left roughly 5 million years ago. From the southern half of the world there are two more. The Magellanic Clouds hanging near the band like torn pieces of it. 4 smudges. Everything else you can see is home. So that is the sky as your eyes report it. A few thousand-year stars. All of them in one small room of one galaxy. A soft band of the rest of that galaxy seen edgewise. And a handful of gray smudges. Our galaxy holds a few 100 billion stars. Nobody knows that number closely, and the honest range runs from about 100 billion to 400 billion. Because most of those stars are small and dim and are counted by weighing the galaxy rather than by looking at them. You can see essentially none of them. A few thousand out of a few 100 billion. If our galaxy were a city of 200 million people, you would know 9 of them by sight. 9 faces out of 200 million. And the city carries on past them in every direction, street after street of it. And that is where the night begins to move. Because the crowd overhead is not a crowd. What looks like a packed field of light is a small handful of near things standing in front of something else, and it is that something else that we are going to walk into. The points are real. The fullness is an accident of what the eye can reach. Your eye has been handed a bright close sample against a black background, and it's drawn the obvious conclusion from the two of them. And that conclusion turns out to be wrong in a way that took careful people several centuries to work out. There is no hurry about it, and we will get there slowly and in order, which leaves the small matter of what this is, and it is a slow walk outward. We begin with the sky above your bed, and we go out past the nearest stars, past the material lying between the stars, out to the shape the galaxies make once enough of them have been mapped, and we finish inside a quiet and measurably empty region. That takes about 2 hours, and nothing in it asks anything of you. Nothing needs remembering, and nothing builds on anything you might miss. And if you are asleep before the second stop, you will have used this exactly as intended. The voice carries on regardless, and it gets quieter as it goes. A word about the emptiness itself, since it is the subject of the whole night. Spending 2 hours on nothing sounds like a cold way to spend it. It is not. The emptiness is the reason the sky overhead is dark enough to see through it all, and the reason the ground under your bed has held the same orbit for 4 billion years. Empty space is a kindness. We will come back to that at the very end, once it has been earned. There is one habit worth mentioning before we set off. Enormous distances are useless when they are spoken out loud. A figure like 40 trillion kilometers does nothing at all inside the mind, so all night I will hand you something small enough to sit on a table, and then the gap beside it. Here is the first one of the night. If the sun were a grain of sand on the table in front of you, the next grain, meaning the nearest other star, would be about 7 kilometers away. Everything between those 2 grains is nothing whatsoever. 2 grains and 7 kilometers of table between them. And that is the crowded part. That is the busy corner, the local neighborhood, the stretch of sky your eyes have been calling full. The walk goes outward from here, and the further out it goes, the more table there is. Stay with the table a little longer, because 2 grains and 7 kilometers is only the beginning of what that model does. Keep the scale exactly as it is. The sun stays a grain of sand, and the nearest other grain stays 7 kilometers off. And now, ask how much table you would need to lay out the rest of the galaxy at the same ratio. The answer is that the table becomes a continent. At 1 grain of sand for every star, and the spacing held honestly all the way out, our galaxy would cover something close to the whole surface of a small country, with a few 100 billion grains scattered across it and kilometers of bare wood between almost every neighboring pair. Not a heap of sand. Not even a thin layer. A continent of empty table with a sparse dust of grains on it. And that is the structure everyone has been calling a crowded sky. The numbers behind that are worth saying slowly, because they are the whole of the point. Our star is about 1.4 million kilometers across, which is large enough that 1 million Earths would fit inside it. The distance to the next star is about 40 trillion kilometers. Divide one into the other, and the gap is roughly 30 million times the width of the thing sitting at the end of it. There is no ordinary object with proportions like that. If you shrank the sun to the size of a full stop on a printed page, the nearest other full stop would sit about 10 kilometers away, with nothing but blank paper in between. The page would have to be the size of a city before the second mark appeared at all. So the stars are not spread through space. They are suspended in it, very far apart, and the space is what there is most of. Try to give that a volume rather than a distance, because volume is where the ratio becomes difficult to hold. Take a sphere of space centered on the Sun and drawn wide enough to reach the nearest star. Inside that sphere sits one star and a handful of planets and a scatter of ice and rock. Everything else is vacuum. Work out how much of the sphere the Sun actually fills, and the answer is a fraction with more than 20 zeros after the decimal point before the first real digit, which does nothing useful in the mind and needs converting into something a person can picture. Here's the conversion. Shrink that whole sphere of space until it is the size of the Earth, and the Sun at its center becomes a ball about 22 centimeters across, one object the size of a beach ball, alone at the middle of a planet with nothing else anywhere inside it. And that is a densely populated region by galactic standards, because we sit in a spiral arm where the stars are relatively close together. The same arithmetic, done for the galaxy as a whole, gives an answer that sounds like a mistake. Add up the volume of every star in the Milky Way, all few hundred billion of them, and compare it with the volume of the disk they sit in. The stars come to a fraction so small that written out it has more than 20 zeros before the first real digit. Written as a fraction of the whole, matter rounds to zero. The galaxy is not a collection of stars with gaps in it. The galaxy is a very large volume of nothing with an extremely thin sprinkling of stars distributed through it. And the nothing is not a gap between the real things, but the overwhelming majority of what is actually there. There is a way of testing that which anyone can follow. Imagine standing anywhere inside the galaxy, choosing a direction completely at random and firing something in a perfectly straight line, not aimed, just released. The question is what it hits, and the honest answer is that it hits nothing at all. Not in 1,000 years of travel, not in 1,000,000, not in the entire time the galaxy has existed. The chance of a random straight line intersecting a star is so small that you could fire in every direction for the age of the universe and expect to miss every time. Space is not a shooting gallery. Space is very nearly a perfect void with a few lit specks in it, and a line drawn through it at random will find the specks essentially never. Our own small corner is built the same way, and it is worth noticing before we go outward. Because most people picture the solar system as a reasonably busy place. 8 planets, a good many moons, a belt of asteroids, comets on long loops. It sounds populated. Add up the volume of every solid object orbiting the Sun, every planet and moon and rock and grain of ice, and then compare that total with the volume of space those objects move through, and the matter comes to a vanishingly small fraction of the whole. The asteroid belt is the clearest case. It has a fearsome reputation, and it is very nearly empty. So thinly populated that every spacecraft ever sent through it has crossed without incident. And the standard problem for a mission that wants to visit an asteroid is not avoiding them, but finding one. The gaps here are just small enough to cross. That is the difference, and it is the only difference. Light makes the trip to the next star in a little over 4 years, which is quick enough to feel almost reasonable. Matter is another matter entirely. The fastest object our species has ever launched would take something like 18,000 years to cover the same distance. The probes actually leaving the solar system now move at around 17 kilometers every second. And they would need more than 70,000 years if any of them happened to be pointed at a star. None of them is. Those craft launched in the 1970s. They have been traveling ever since, faster than anything else we have made, and they have covered roughly a 500th of the way to the nearest star. That is the honest measure of the gap, not a number of kilometers. A working lifetime of the fastest thing we can build, spent covering a fraction of 1% of the one step. And it does not stop at the large scales, which is the part that tends to stay with people. Pick up the grain of sand from the table. It feels solid, and it is not. Almost all of its volume is empty space as well, because an atom is a very small, dense nucleus with a great deal of nothing around it. Scale one nucleus up to the size of a marble, and the nearest electron would sit a couple of 100 meters away, with the whole of that distance empty. Solidity is a force, not a filling. What stops your hand passing through the table is not that the table is full, but that electric fields resist being pushed into one another. And the sensation of a solid surface is really the sensation of a field holding you off. So the grain is mostly nothing. The gap between the grains is nothing, and the continent the grains are scattered across is nothing, almost all the way through. Emptiness is not a feature of the large scale. It is the ordinary condition of matter at every size we have ever looked at, and the solid world you are lying in tonight is a very thin arrangement of forces that happens to be arranged closely enough to hold together. This is why the sky is safe. Consider what happens when two galaxies meet, which is a thing that genuinely happens and has been photographed many times. Two systems of several 100 billion stars each drift into one another over hundreds of millions of years. And the pictures look violent, with long torn streams of stars pulled out into bridges and tails. Something dramatic is clearly going on, and yet almost no stars collide. Not a few. Very close to none. The stars pass through the opposing galaxy like two clouds of midges crossing a valley, each insect sailing through the gaps in the other swarm without ever meeting one, and the whole encounter is settled by gravity rearranging orbits rather than by anything striking anything else. The gas clouds do collide, and they light up with new stars where they do. The stars themselves simply slide past. Two galaxies can pass through each other, and the odds of any single star hitting another star remain effectively zero. That is not a fact about how careful the stars are. That is a fact about how much room there is. The room is also what keeps our own arrangement steady. Every planet here has been going around the sun for 4.5 billion years on a path that has barely changed, and it can do that because there is nothing nearby to disturb it. No other star passes close enough to matter. Nothing tugs the Earth off course, nothing arrives to pull Jupiter out of its orbit, and the whole clockwork holds for billions of years at a stretch because the nearest outside influence is 40 trillion kilometers away and is therefore, in practical terms, not there. A crowded galaxy would have no stable planetary systems in it. Orbits would be disrupted, worlds would be flung loose, and nothing would last long enough for anything slow and complicated to happen on any of them. So the emptiness is not a shortage. It is the condition. It is the reason a planet can hold a steady orbit for long enough to cool and settle and grow an ocean and eventually put someone on a lawn at night looking up at the very gaps that made all of it possible. The distance that makes the sky look empty is the same distance that makes the sky quiet. And a quiet sky is what a slow process needs. There is one more consequence, and it runs the other way. The gaps are also why we know so little by direct means. Nothing has ever been sent to another star, and nothing will be for a very long time, because the fastest object our species has ever launched would need tens of thousands of years to make the crossing. Everything we know about other stars arrived as light. Not samples, not visits, light, which crosses the gap for free because it is the only thing that can, and which brings a genuinely astonishing amount of information with it if you know how to take it apart. The emptiness is therefore a filter as well as a shelter. It keeps us apart from everything and it lets us see almost all of it. And those two facts are the same fact seen from different ends. Now hold the scale one more time before we leave it. A grain of sand, 7 kilometers of table, a continent of bare wood, and a few 100 billion grains lost on it. That model is honest at the scale of one galaxy. But the galaxy is a grain too. It sits in a far larger arrangement with far larger gaps, and the same question that opened this table can be asked again at every scale above it. And the answer keeps coming back the same way, only more so each time. The gaps between the stars are enormous, and they are the small ones. The emptiness leaves a mark, and anyone who steps outside after dark has already seen it. The sky is black. Between the stars there is nothing to look at, and the gaps are far wider than the points of light sitting inside them. That blackness is not decoration, but a measurement taken by every pair of eyes that has ever looked up, and it quietly rules out an entire way the universe might have been arranged. Suppose, for a moment, that space went on forever in all directions. Suppose it had always existed, with no beginning, and that stars were scattered through it evenly, at roughly the same spacing everywhere, burning steadily and endlessly the way a fire never really does. Nothing about that picture sounds strange, and for most of recorded history, it was the sensible assumption, the one a careful person would make before there was any evidence either way. And it fails immediately. The reason sits in plane geometry, so take a line of sight, any line, straight out from the eye into the dark, and follow it. In an endless field of stars, that line has to end on a surface. It might travel a long way first, but given enough distance, it will always run into something bright, because every direction eventually finds a star, and an endless supply of stars gives endless chances for that line to be stopped. Think of a wood in winter, the trees bare and evenly spaced, going on without an edge. Stand among the trunks and look out level in any direction at all. Close by, you see gaps. Farther out the trunks overlap, and farther still they close into a solid wall of bark with no daylight left in it anywhere. The wood does not have to be dense. It only has to be endless. A sky full of stars, going on forever, behaves the same way. There is an objection that seems to fix all of this, and it does not. Distant stars look fainter. A star twice as far away delivers a quarter of the light, which feels like it should settle the matter. But the same doubling of distance buys a great deal more room, and the shell of space at that radius holds 4 times as many stars, so the extra number cancels the extra faintness exactly, and every shell gives as much light as the one inside it. Add up endless shells, each giving the same, and the total has no limit. The sky should be a wall of light, not bright like a full moon, and not bright like a city seen from a hill, but as bright as the surface of the sun itself, in every direction, with no shade to be found anywhere on the ground below. Every window would be a lamp, and every wall would be lit from both sides, and there would be nowhere on the planet to stand in the shade of anything. There would be no night, and no shadow either, because a shadow needs somewhere darker to fall. It would be an even lit ceiling all the way round, and the ground beneath it would sit at one steady temperature, day and night alike. That is not the sky anyone has. So one of those assumptions is wrong, and the darkness overhead is the evidence saying so. Astronomers noticed the trouble a long time ago, well before anyone knew what a galaxy was, or that the universe had a history at all. The argument is old and simple, and it needs no telescope at all. It sat unresolved for centuries, and for most of that time the favored escape was dust. If clouds of dark material lay between here and there, soaking up the light from the far stars, then the bright wall would be hidden, and the sky could stay black. A tidy idea, and it does not survive much thought. Dust that absorbs light does not simply hold on to it, it warms up. And anything warm radiates, which means that after long enough, every grain of that dust would be glowing with the light it had swallowed, and the sky would come out just as bright as before, only in a longer and redder form. Hiding light inside matter is temporary, and given enough time, the books always balance. The answer turned out to be about time instead. The universe has an age. It began roughly 13. 8 billion years ago, and that single fact removes the endless supply of stars the whole argument depended on, because light travels at a fixed speed and has only had so long to be on its way. A star 20 billion light years off may well exist, and its light is still in transit. It has not arrived, it will not arrive tonight, and for the purpose of lighting up the sky above a bedroom window, it may as well not be there. Nothing about that is a trick of perspective, only a matter of arrival times. The far trunks are still out there in the wood. Their light is simply still on its way, and nobody has been standing here long enough for it to arrive. That shortage of time draws a boundary around what can be seen, and the boundary is not a wall or a surface or a place anyone could travel to. It is only the distance light has managed to cover since there was light to travel. Beyond it, nothing has reached us, not dimly, not faintly, not at all. There are galaxies out there tonight, ordinary ones, full of ordinary stars, that have never sent us anything and will not for a very long time. The boundary is not fixed either. It grows by 1 light year every year, quietly, with no event marking the change, and each year a thin new shell of the universe comes into view for the first time. The number describing that boundary is larger than the age suggests. Light has been traveling for 8 billion years, and yet the farthest material anyone can see now sits about 46 billion light years off, because space itself stretched while the light was crossing it and carried the source further away. The light took the short trip, and the ground underneath it kept lengthening the whole way. That stretching does something else, and it matters for the darkness. A wave of light crossing expanding space gets pulled longer along with everything else. Its color slides. Blue becomes green, green becomes red, and red becomes something the eye has no name for and no cell to catch. Light that leaves a distant galaxy as an ordinary yellow glow, the same color as sunlight on a wall, can arrive here shifted so far down the range that it lands in the infrared or past that into microwaves, carrying the same message at a lower pitch. The energy carried per wave drops as well, and stretched light is weaker light. The far parts of the sky are therefore dimmed twice, once by the plain shortage of time and once by the stretch, and what does get through arrives too long and too faint for eyes. How much of the dimming to credit to the stretching and how much to the simple lack of time is still argued over by the people who work on it, and the usual verdict is that age does most of the work. Stars help the case along because they do not burn forever either. A star has a fixed amount of fuel and a fixed span, and even a universe with no beginning would need its stars replaced constantly to keep an endless wall of light supplied. Nothing in the sky is that patient. All of that accounts for the darkness. All of that accounts for the darkness in visible light. At longer wavelengths, the same sky is not dark, and it took a radio dish to notice. Point a radio dish at any blank patch of sky, somewhere with no star and no galaxy and nothing cataloged at all, and a signal comes back. It comes back from every blank patch. The whole sky is glowing at 7 Kelvin, roughly 270 degrees Celsius below the freezing point of water. Colder than anything on this planet outside a laboratory. 2 engineers found it in 1965 by accident while trying to clear a faint hiss out of a radio antenna in New Jersey. They checked the wiring, they cleaned out a pair of nesting birds, they pointed the horn in every direction they could manage, and the hiss stayed exactly the same strength no matter where they aimed it, which is the one result that cannot be caused by anything local. The strength was the same in every direction, which ruled out the ground and the antenna and the galaxy alike, and left a signal spread evenly through the whole of space. The measurement has been repeated since from mountaintops, from balloons, and from satellites parked well beyond the moon, and every time the answer comes back the same. What they had picked up was the early universe cooled down. For a long stretch after it began, everything was hot enough to shine, not in one place, but in every place at once, a fog of light with no gaps in it and no dark direction anywhere to look. That fog thinned and let its light go, all of it, in every direction, and the light has been traveling since. It has been stretched by roughly 1,000 times on the way, dropped from the glare of a furnace to a whisper in the microwave band, and spread thin beyond ordinary description. But it is still arriving. It arrives tonight, through the window, through the wall, through the pillow, at a rate that has not changed in any way a person could notice. The old picture was not wrong about the wall of light. The wall is there. It surrounds this room on every side, complete, without a single gap, and it is the last thing anything can see in any direction. The old picture only had the temperature wrong. It expected the surface of a star and found something far gentler. If human eyes worked at those longer wavelengths, night would not look like night. It would look like a softly lit room with no lamp in it. Even brightness, edge to edge, above the horizon and below it, the same towards the city and the same away from it, matched from one side of the sky to the other to within about 1 part in 100,000. No shadows, because there is nothing for the light to fall behind. No source, because all of it is source. The stars would be invisible against it. That is the part worth holding on to. The darkness is not a property of space. Darkness is a property of eyes. Eyes were built for daylight on a planet, not for the whole of what light can be. Hold a grain of sand at arm's length and cover one of the black gaps between 2 stars. The grain hides a patch of sky that looks like nothing at all. A long enough exposure on that same patch turns up several thousand galaxies, stacked back through most of the age of the universe, every one of them shining the entire time anybody stared straight past it. The dark was never empty of things. It was only empty of things bright enough. Human sight opens onto a narrow strip of a very wide range, and the strip happens to fall in the one place where the sky holds almost nothing, which is why night looks like an open window rather than a lit ceiling. And that narrow strip is the whole reason astronomy is possible. A bright sky would be a closed sky. If every line of sight ended on a glowing surface, there would be nothing to see past, no gap to look through, and every star and galaxy would be washed flat against a background as bright as itself. The dark is what makes the sky transparent. A dark sky is a quiet one, and quiet is what allows small signals to be noticed at all. Everything anyone has ever learned about anything beyond this planet arrived through that gap, and it arrived only because the gap was there to arrive through. The darkness does a quieter kind of work as well, closer to hand. A cold sky is somewhere for heat to go. Warmth leaves the ground at night and climbs, and because there's nothing overhead sending an equal amount back down, it keeps going and does not return. That is why a clear night is colder than a cloudy one. It is why frost settles on the roof of a parked car and not on the pavement under a tree. It is why a desert loses in one night everything it gained all day. Every warm thing on this planet is quietly leaking heat into the dark all the time, and the dark accepts it without ever filling up, because it is very large and very cold and it has room for all of it. The dark is doing that for the whole planet, every night, without any attention from anyone. That is a good arrangement, and nothing here would be stable without it. A sky that shone would hold the ground at one temperature forever, and no surface anywhere would ever get the chance to cool and settle and stay still long enough for anything slow and complicated to begin. The emptiness overhead is what allows an evening to feel like an evening. Cool air, a dark window, a bed, the sky doing what it does, which is mostly nothing, very evenly, in every direction at once. Though the gap between the stars is dark and cold, it is not quite the perfect nothing it appears to be. There is something in it, very little, spread very thin, and worth looking at closely. What is in it is gas, mostly, and it is thinner than almost anyone expects. The space between the stars is not a vacuum in the strict sense, because a strict vacuum would have nothing in it at all, and this has something. Call it about 1 atom in every cubic centimeter. That is the rough figure for the ordinary space between stars in a galaxy like ours. And a cubic centimeter is a very small box, about the size of the tip of your little finger. one atom in a box that size. For comparison, the air in the room where you are lying now has something like 25 million atoms in the same volume. That makes the air around you denser than interstellar space by a factor with 19 zeros after it, and the difference between those two conditions is far larger than the difference between your room and solid steel. That comparison is worth turning over. Air and stone feel like opposites. But on the scale that runs from empty to full, air and stone sit almost on top of each other, and the space between the stars is somewhere else entirely, far below both of them, in a range that has no everyday example at all. The good vacuum chambers built on this planet do not reach it either. A serious laboratory vacuum, the kind used for delicate physics, gets down to perhaps 100,000 atoms per cubic centimeter after a great deal of pumping and baking and patience. That is a genuine achievement, and it is still 100,000 times denser than the ordinary space just outside the solar system. No pump has ever produced interstellar conditions. The emptiest thing we can manufacture is crowded compared with the average corner of our own galaxy, and the emptiest place we know of is emptier still by a wide margin. So when the word empty gets used tonight, this is the sense of it. Not nothing. Nearly nothing, which is a different and stranger thing. The atoms that are there are almost all hydrogen, the simplest and oldest kind, with about 1 atom in 10 helium and a very small trace of everything heavier. Those heavier atoms were made inside stars and released when the stars died, so the thin gas between the stars is slowly getting richer as generations of them come and go. There is dust as well, and the word is misleading. The material is not household dust, but grains of carbon and silicate a fraction of the width of a human hair, and there is roughly 1 grain of it for every 100 million atoms of gas. Almost nothing, again. And yet it is the dust that produces the dark lanes cutting across the bright band of the galaxy, because a great enough depth of almost nothing will still block light, and those lanes are not gaps in the stars, but curtains drawn in front of them. A single grain of that dust would be invisible to you. A few thousand light years of it will hide 100 million stars completely. There are denser regions, and even they are thin. The gas is not spread evenly. It gathers into clouds, and the coldest and heaviest of them are called molecular clouds, and these are the places where new stars form. A molecular cloud might reach 1 million particles per cubic centimeter in its dense cores, which is 1 million times the ordinary figure and sounds substantial. It is, by the standards of this story. That is around 10 times denser than the best vacuum ever pumped out in a laboratory, and it is the closest thing to a crowd anywhere in the space between stars. And it's still around 10 million times thinner than the air in your room. The densest nursery in the galaxy is emptier than anything you would call empty. They are simply very large, and largeness is what lets them gather enough material to make anything at all. Size is doing the work everywhere in this story. A thin thing that is big enough behaves like a dense thing. Take a nebula, one of those enormous glowing clouds that photographs so well. It looks solid. It looks like colored smoke you could put your hand into and feel. And if you flew through one, you would notice nothing whatsoever. No resistance, no fog, no change in the view, because the material is spread across tens of light years, and at any given moment there would be almost nothing near your face. The visible shape only exists because you are looking through an immense depth of it, and the faint glow of every part is adding up along your line of sight. Seen from inside it is not there. Seen from very far away, It is a landmark. There's a way of describing the thinness that gives it a distance rather than a count, and it is called the mean free path. It means the average distance a particle travels before it meets another one. In the air around you, that distance is tiny, a small fraction of the width of a hair, which is why air behaves as a smooth substance and carries sound and pushes back against your hand. In ordinary interstellar space, the same distance is measured in something closer to hundreds of millions of kilometers. An atom out there can travel further than the gap between the Sun and Jupiter before it meets a companion, and it can do that for tens of thousands of years at a stretch. Which is why nothing out there carries sound. Sound needs particles close enough together to pass a push from one to the next, and space has no such crowd in it, so a very loud event in a nebula makes no noise that anything nearby could ever hear. Now widen it out to the universe as a whole, and the number gets smaller again. The average density of everything, taking all the galaxies and all the space between them and smearing the whole lot out evenly, comes to somewhere around 6 protons per cubic meter. Not per fingertip, per cubic meter, a box you could sit inside. 6 particles in a volume that would hold a person, and that is the honest average of the entire universe, including every star and every planet and every galaxy in it. On that measure, our own thin interstellar gas, at 1 atom per cubic centimeter, is over 100,000 times denser than average. We live in a dense place. The galaxy is a crowded exception, and even here nothing you can point at feels anything like full. Thinness also changes what temperature means, and this is where the everyday word stops working properly. Space is described as cold, and the description is fair, but not for the reason most people assume. Cold usually means a substance that will draw the warmth out of you, the way cold water does, and cold water is efficient at it because it is dense, and every part of it touching you carries heat away. Interstellar gas cannot do that. There's nothing like enough of it in contact with anything to conduct warmth anywhere. So an object out there does not get chilled by its surroundings in the ordinary sense, and it loses heat only by radiating it away, which is a far slower business. This is exactly how a vacuum flask keeps tea hot on a cold morning. The gap in the wall of the flask has almost nothing in it, so there is nothing to carry the heat across, and the emptiness works as insulation. Space is a vacuum flask with no outside. There is still a floor to how cold anything can get out there, and the floor is set by the radiation left over from the early universe, which fills every cubic centimeter and sits at about 7 Kelvin. That is a little under 271 degrees below zero on the Celsius scale. Nothing in deep space, left alone and shaded from every star, cools below that figure, because the faint glow of the early universe keeps warming it back up to the temperature of the glow itself. A very old warmth, spread absolutely evenly, and it is the last thing standing between deep space and absolute zero. We have also measured all of this directly once, which is worth saying because so much of tonight is measured from a distance. 2 probes launched in the 1970s have crossed out of the sun's own bubble of wind and into the interstellar gas beyond it, and their instruments reported the change as it happened. Inside the bubble, the particles were sparse and hot and streaming outward from the sun. Outside it, the gas was denser and colder and moving differently. That boundary is a real edge with a real crossing, and 2 objects built by people have gone through it and sent a reading back. Which brings up something that will matter later tonight. The sun is not sitting in average interstellar gas at all. Our whole neighborhood, out to roughly 300 light years in most directions, sits inside a cavity in the gas where the density is much lower than the galactic average. Perhaps 1/10 of it. Astronomers call it the local bubble. The best explanation is that a series of stars exploded in this region over the last 10 to 20 million years, and their expanding shells swept the gas outward, leaving a hollow with hot, thin material inside and denser walls around the edge. The sun happens to be drifting through that hollow at present. We did not make the bubble, and we are not fixed inside it. We wandered in, and in a few million years we will wander out. So the emptiest ordinary space we know of is the space immediately around us, and we are living in a hole that something else dug. Hold on to that shape, because it repeats. A region emptier than its surroundings, with the observer inside it, is going to come up again at a scale enormously larger than 300 light years. And the question of whether we happen to sit in an unusual pocket turns into one of the more interesting arguments in modern astronomy. The near nothing is not idle, though, and this is the part that surprises people most. The volume between the stars is threaded with things that are not atoms. Light fills it everywhere, both starlight and the far older, far colder radiation left from the early universe. It carries magnetic fields, weak but reaching across whole spiral arms and shaping how the gas flows and where it gathers. Fast particles cross it constantly, arriving from exploded stars and from further out than that, and it is streaming with neutrinos, which barely interact with anything and pass through matter as though it were not present. Something like 60,000 million of them are passing through every square centimeter of your body every second, right now, from the sun alone, and essentially all of them will go straight through the planet and out the other side without touching a thing. So the empty space is quiet. And it is not inert. It is thin and it is busy, and those two can be true at once. That is worth holding on to, because the emptiness in this story is never a blank. It is a real physical condition with a temperature and a chemistry and a set of behaviors, and the reason it matters is that it is the normal state of the universe. Matter is the anomaly. The stars and the planets and the people are small dense knots in a medium that is almost perfectly clean. If you wanted to describe the universe honestly by describing what most of it is like, you would spend nearly all of your time describing this thin, cold gas and mention the stars only in passing. One atom in a box the size of a fingertip, cold, quiet, faintly lit, and stretching between every star you have ever seen. Distance is the thing a photograph cannot record, and the same problem returns once the scale gets larger than a single galaxy. Step back far enough, and the stars stop being separate things. A whole galaxy shrinks to a smudge of light, then to a point, then to a single dot on a photographic plate. Just a dot. And once a galaxy is only a dot, it can be counted and plotted and compared against its neighbors, which is exactly what astronomers set about doing more than a century ago with glass plates and a great deal of patience. The counting came first, and it went on for decades. Galaxies had to be recognized as galaxies before anything else, and that only settled in the 1920s. When it became clear that the faint spirals were separate systems of stars lying far outside our own. Before that, they were smudges, filed alongside gas clouds. The question the counting was built to answer sounds almost too plain to need a telescope. Either the galaxies were spread evenly across the sky, or they were gathered into groups. The answer that came back looked like both at once, which is usually a sign that a measurement is missing something. There were obvious clumps, dozens of galaxies sitting close together in one direction, and long stretches where the field seemed thin. But a photograph of the sky is flat. It records direction and brightness, and nothing else. Two galaxies can sit side by side on the same plate, while one of them lies 3 times further away than the other, and no amount of staring at the picture will separate them. The sky is a projection. Everything in it is pressed onto a single surface, near and far together, and the depth that would tell you how the galaxies are really arranged is thrown away in the act of looking. For a long time then, the arrangement stayed hidden. What the map was missing was distance, the one thing a photograph can never supply. Distance is the hard measurement in astronomy. And for galaxies, there is one tool that works at almost any range: stretched light. Space has been expanding for 13.8 billion years, and light traveling through expanding space is stretched along with it, so that waves which left a galaxy short and blue arrive longer and redder than when they set out. The stretch can be measured precisely, and that is what makes the method work. Every element leaves a signature in a spectrum, a set of narrow lines at wavelengths that never vary in a laboratory. Spread a galaxy's light into a spectrum and those same lines appear, sitting further toward the red end than they ought to. Measure how far they have moved and you have the amount of stretch. More stretch means more expansion since the light left, which means more time in transit, which means a greater distance. That quantity is what astronomers mean by a redshift, and it is the backbone of every large map ever made. It is the one number that turns a flat picture into a map with depth. The work was slow at first because a spectrum needs far more light than a photograph does, and a faint galaxy had to be held in the same position for hours while its light dribbled into the instrument a few grains at a time. One galaxy an evening. At that rate, a serious map was out of reach, and for decades the catalogs held plenty of positions and only a scattering of distances. Then the instruments changed, and the arithmetic of the whole enterprise changed along with them. Fibers were laid into the focal plane of a telescope, one fiber for each galaxy, feeding 100 spectra at once into the same detector, 100 galaxies an hour. The surveys that followed measured positions and distances for tens of thousands of galaxies, and then for hundreds of thousands, and then for millions, working through the sky in narrow strips and building the map slice by slice. The largest of them, the Sloan Digital Sky Survey, has been at the work for more than 20 years and now holds spectra for several million objects. The method has not changed much since. Point the telescope at a strip of sky. Gather a spectrum for everything in it down to a chosen faintness. Turn each redshift into a distance and set that galaxy in its place inside a model with 3 dimensions. Then move along to the next strip and do it again. A map of the universe gets built the way a darkroom is surveyed, one line of sight at a time. The first proper slices came in the late 1970s and the early 1980s. They were thin wedges, a narrow band of sky taken out to a fixed depth, with every galaxy in the wedge set at its measured distance. Nobody involved knew quite what the finished wedge was going to look like. And even scattering was the reasonable guess. A fine haze of dots filling the wedge with a few clumps here and there. The expectation of randomness was not lazy. It was what a smooth beginning seemed to imply. When the first wedges were plotted, the dots lay in lines rather than in an even haze. Long chains of galaxies ran across the wedge, with dense knots where the chains met, and almost nothing inside the shapes the chains enclosed. Long chains of galaxies ran across the wedge, and where the chains met, there were dense knots, and inside the shapes the chains enclosed, there was almost nothing at all. Empty rounds tens of millions of light years across, galaxies strung around their rims. It looked drawn rather than sprinkled, as though the lines had been ruled in first, and the galaxies had settled onto them afterwards. And it held up. Every later survey, deeper and wider and better calibrated, found the same shapes at every scale it could reach, and the arrangement is now among the best measured facts about the large universe. The shape has a name, and the name has lasted because it describes the thing exactly. The cosmic web. Matter is gathered into long, thin filaments, threads of galaxies running for hundreds of millions of light years. Filaments join into sheets and walls where threads have spread out into a plane. Where several filaments cross, matter piles up into a cluster, a knot of hundreds or thousands of galaxies held by their own gravity and by the far greater mass of matter we cannot see. Those knots are the densest places there are. A cluster is the most crowded thing the universe assembles. Even so, crowded is a relative word here. The galaxies inside a cluster are still parted by gaps that dwarf their own widths, so the crowding is a matter of counting, not of contact. Between all of it, in the volumes the threads and the sheets enclose, the count of galaxies falls away to almost none. The standard picture for this is foam, and it is a good one. Fill a sink with soapy water and look at the froth on top. The soap sits in the thin films between the bubbles, and it collects along the lines where three films meet, and it pools at the corners where those lines run together, and the inside of every bubble is only air. That froth is the arrangement, near enough, and the likeness holds part for part. The films are the sheets, the lines are the filaments, the corners are the clusters, and the air inside is most of the volume. The resemblance is rough, and that is worth saying plainly. Real bubbles have skins that hold them closed, and the web has no skin and no wall to keep anything in or out. Nothing is sealed. The filaments fray, the sheets are ragged, and the empty regions leak into one another wherever the threads run thin or stop. But the eye takes the point at once, which is the whole reason the comparison has lasted so long. That leaves the matter of how a smooth beginning turned into a shape like that. The answer is gravity and time, and very little else. Measurements of the oldest light show a universe that started out almost perfectly even, with the density varying from place to place by about 1 part in 100,000. That is nothing. A room whose air varied that much would feel identical from wall to wall. But gravity does not treat a small difference as nothing, because a region slightly denser than its surroundings pulls slightly harder, and so it gathers a little more matter, and the gathering makes it denser still, and the pull grows along with it. The advantage compounds, slowly at first and then with real momentum. Over hundreds of millions of years, the slightly full places become properly full, and the slightly thin places are drained by them. Matter flows downhill in the gentlest possible sense of the word. It leaves the thin regions and joins the dense ones, never quickly, but without ever stopping, across billions of years. The order of the collapse is what produces the shape. A rough patch of matter is never a perfect sphere, so it is always a little shorter along one direction than the others, and it gives way along that direction first. It flattens before it does anything else. A blob becomes a sheet. The sheet then gives way along its next shortest direction and draws itself into a thread, and the thread runs matter along its length into the knots at either end, so that one kind of collapse repeated 3 times over yields sheets and filaments and clusters in that order. The web is a record of the order in which things fell. Most of the falling was done by matter that gives off no light. It outweighs the visible matter by roughly 5 to 1, and it built the frame that the gas and the galaxies later settled into. What that matter actually is remains unsettled. That is a genuinely open problem in physics, and it would be wrong to present it as anything else. But its behavior under gravity is understood well enough to model, and when the model is run forward from that nearly smooth beginning, it grows filaments and sheets and knots and empty regions, at the right sizes and in the right proportions, with nobody putting them in by hand. The simulation and the survey can be laid side by side. They look like the same object. That agreement is the strongest reason to trust the picture, and it's why the web is spoken of as measured rather than imagined. Which brings the account round to volume, and volume is the part that is easy to pass over. Galaxies live in the threads and the knots. Almost all the light in the universe comes from those places, and almost all the matter that has ever done anything at all is there. But the threads and the knots are thin. Take the whole mapped universe and ask how much of its room lies inside a structure and how much lies outside one, and the structures lose by a wide margin. Most of the volume is in the empty parts, not a little more than half. Most estimates put it somewhere from 60% to 80%, and some of them go higher than that. The web is a shape drawn across a far larger amount of nothing. The spread in those numbers is not sloppiness, and it deserves a plain explanation. An empty region has no edge. Density does not drop off a cliff at some line and then stay flat inside. It thins gradually outward from the filament, reaches a minimum somewhere in the middle and rises again on the far side toward the next thread along. The boundary is therefore a choice somebody makes, not a feature waiting to be found. One team draws it where the density falls to a fifth of the average, and another draws it at a third, and a third group fits the shape by a different method entirely. And each of those choices moves the final answer by tens of percent. The pattern itself is not in dispute anywhere, and no careful survey has ever failed to find it. Only the bookkeeping is. Nobody has settled on a single definition, and the honest way to put it is that the empty regions hold the clear majority of the volume, with the exact figure depending on where the line gets drawn. Bring it down to something in the room. Set a cluster of galaxies on the table in front of you as a coin. On that scale, the next coin sits about a meter away. The thread of galaxies joining them is finer than a length of cotton, and all the rest of the space between those two coins, the whole width of the table, is nothing that would show up at all. The coins are the parts we photograph and name and write papers about. The table is what the universe is mostly made of. That arrangement is a cooperative one. The emptiness is what lets the structure exist, because matter can only gather in one place if it is leaving another, and every filament in the sky is built from the material that some quiet region gave up. The full places and the empty places are two halves of one process, and neither of them could have happened without the other. A full place and an empty place made together. The same emptiness is why the view works at all. Light can cross those regions for hundreds of millions of years without meeting anything that would absorb it, or bend it, or scatter it away. The map only exists because most of what lies between us and the far galaxies is clear. We can see the shape because the gaps are honest. So the web is not really the subject anymore. The threads have been traced and counted, and the knots have names and catalogs of their own. What has not been described is the other part, the volume between. Those regions are not featureless, and they are not all alike, and some of them run far larger and far emptier than the rest. And they can be measured and mapped and walked through in the same patient slice by slice way. The rooms have sizes, and they are the larger half of the house. The filaments and the walls are the parts we map. The gaps between them are the parts we tend to pass over. They deserve better. Because when a survey plots every galaxy it can reach, the bright threads come out clearly, and the eye follows the threads and reads the whole picture as a net, when most of what has been measured is the space that the net encloses. The space inside the net has a name of its own. Cosmologists call the largest of those gaps voids, and the word does a great deal of quiet work because it promises nothing whatsoever, while the truth is closer to almost nothing. A void is a region where the density of matter has fallen well below the average for the universe. Not zero. Just low, and low across a distance so large that the reading stays low wherever in the region it is taken. The smallest of them measure about 30 million light-years across. The largest run out to several hundred million. They were not carved out of anything, because nothing came along and removed them. They are the places where matter began slightly thin and then went thinner, since gravity moves material from thin places toward thick ones, and never the other way around. Over time, the thin places emptied themselves out. Over 13 billion years, the drift went one way, out of the middle of every void and into the walls around it, which is why the walls are sharp and the middles are quiet. The pattern behind all of it is very old. It was set in the first fractions of a second, as ripples in density so faint that they show up in the background radiation as differences of one part in 100,000. Everything since has been those ripples growing. A shortage became a hole. Now the awkward part. Anyone who tries to say what fraction of the universe is void runs into a definition problem straight away. A void has no edge that could ever be painted on. Density falls off gradually from a wall toward a center, so the boundary is a line that somebody chooses, usually the surface, where the density drops below an agreed fraction of the average. Move the fraction and the answer moves with it. Choose a strict threshold and voids fill perhaps 60% of the volume. Choose a looser one and the figure climbs past 80%. Both of those numbers have been published. Both are correct within their own definitions, and neither is wrong. And the disagreement is not about the universe at all, but about vocabulary. The honest statement is the vague one. Most of the volume of the universe sits in regions with far less matter in them than average, and the exact figure depends on where the line is drawn, which is why careful papers describe a method before they give a number. The clearest example of a void was found by accident. In the late 1970s, a small team began measuring distances to galaxies in the direction of the constellation that hangs off the handle of the Big Dipper and holds the bright orange star Arcturus. The work was slow. Every galaxy needed its own spectrum, its own night on a telescope, its own careful reduction, because a redshift is the only way to turn a dot on a photographic plate into a distance. They expected galaxies at every distance out to the limit of the survey. What they found instead was a gap. Between roughly 600 million and 900 million light-years away, in that direction, the count of galaxies fell to almost nothing and stayed near nothing across an enormous stretch of sky. The result was published in 1981, and it was not immediately believed. A hole that size did not fit what anybody expected the universe to look like. And the natural first thought was that the survey had missed things, that the galaxies were there and simply too faint, or that the sampling had been unlucky. Follow-up work over the next decade settled the question. The region is now called the Great Void, and at roughly 330 million light-years across, it remains the standard illustration of what a large void is. It is not empty. This is the point where popular accounts tend to overreach, because the Great Void does contain galaxies, and later surveys have found many more of them than the first one did. The count now sits at around 60. An average region of that size would hold something in the range of 2,000, and rather more than that if faint dwarf galaxies are counted in the tally. So the shortfall is real, and it is large. A factor of tens, and not a factor of infinity. 60 galaxies in a room built for thousands. There is one further wrinkle worth stating plainly. The galaxies that are in there are not scattered evenly through the volume, but appear to run in a rough line across the middle, which has led to a reasonable suggestion that the Great Void is not one void at all, but several smaller ones that merged. The line would then mark what is left of the walls between them. That reading is not settled either way. But it is also not necessary for the main point, since the region holds a small fraction of what an average patch of the universe holds. The Great Void stopped looking like an anomaly fairly quickly. As the redshift surveys grew through the 1980s, the same pattern turned up in every direction anybody looked, and the holes were not exceptions in an otherwise even universe, but the ordinary condition of it. It was simply the first one large enough and close enough to be impossible to miss. The number is easier to feel from the inside. Put a planet near a star somewhere in the middle of it, and give that planet a clear night and no moon. There would still be plenty of stars overhead. A galaxy in a void is still a galaxy, and its own stars would crowd that sky from within exactly as ours crowd ours. The band of light overhead would look entirely familiar. What would be missing is everything past the edge of that one galaxy. The sky there would be a purely local sky. Nothing like the Andromeda Galaxy, which is a faint smudge findable with the unaided eye from a dark site at 5 million light-years. The nearest other large galaxy would be tens of millions of light-years off, far too small and faint to notice without a telescope. The sky there would be a purely local sky. one galaxy, and then a very long quiet. And the quiet has a size that can be stated plainly. A traveler crossing the middle of the Great Void at the speed of light would go for something like 100 million years between one galaxy and the next one worth the name. Nothing much to pass on the way. No dust worth measuring, no clouds, no remains of anything that came before. A gas so thin that collecting a single atom of it would mean sweeping out many cubic meters, thinner than the space between the stars of our own galaxy by a wide margin, and that space is already close to a laboratory vacuum. The temperature holds at about 7 Kelvin. That is the background radiation and nothing else. The same faint warmth that fills every part of the universe equally, arriving from all directions with nothing nearby to add to it. Cold, level, unchanging. It is a calm place. Nothing arrives, nothing passes close, and nothing changes there because there is nothing near enough to change it. The state it is in now is the state it has been in for billions of years. And crossing the boundary would not feel like anything because there's no boundary to cross. Only a place where galaxies stop appearing as often and then stop appearing at all. No wall, no line, and no door of any kind. Here is the ratio in terms of something in the room. Set a coin on the table beside the bed and let that coin stand in for a galaxy like ours. On that scale, the galaxies in a wall of the cosmic web sit a meter or two apart, near enough to look like a chain of coins laid out along the floor. And a void that size is a clear stretch of floor about 60 meters long, longer than the building you are lying in, with a few coins somewhere near the middle, and nothing else anywhere on it. Not thinned out, just absent. The emptiness also changes how the region behaves, and this is the part that makes voids useful to science rather than merely striking to look at. Expansion turns out not to be uniform in detail. Everywhere in the universe space is growing, and everywhere matter pulls back against the growth, so the local rate depends on how much matter is nearby to do the pulling. In a wall, there's plenty of it. In a void, almost none. A void therefore expands faster than the average, and the difference is small as a percentage and enormous in its effect once it has been compounding for billions of years. Measurements put it at a few percent. A few percent held steady for 13 billion years. That is how a slightly thin region becomes a genuine whole. The voids are still growing at this moment. They grow at the expense of the walls, since a void draws nothing inward while the walls draw material outward from it, which sharpens the contrast between the two with every passing era. The process has no natural stopping point, because every gram that leaves a void leaves it slightly less able to hold on to the next gram, so the thin places thin further while the dense places gather. What we are looking at now is the middle of a very long sorting. Even the light passing through takes note of it. A photon that falls into a wall gains a little energy on the way in and gives it back climbing out the far side. And if the wall has weakened while the photon was crossing, the climb out is cheaper than the fall in. The photon keeps whatever difference is left over. The effect is tiny, and it is entirely real. It has been measured by stacking the background radiation behind thousands of known voids. And the slight temperature shift that turns up is generally read as direct evidence that the large empty regions are growing rather than holding still. The regions are widening, and that faint shift in the background light is the direct evidence of it. The galaxies left behind inside them are different, and the differences are measurable. A galaxy in a void has almost nobody to collide with. Mergers are rare there. Growth by collision is a large part of how the biggest galaxies in the universe became big, so a void galaxy tends to stay modest. A disk of gas and young stars rather than a swollen ball of old ones. They are smaller on average and they hold more cold gas. They are still making new stars at a decent rate, long after galaxies in crowded places have run through their supply and gone quiet and red, bluer, gassier, slower. Living at a pace that the crowded regions gave up on long ago. The reason for that is not mysterious. A galaxy inside a cluster is stripped of its gas by the hot, thin medium it pushes through, and shaken by close passes from its neighbors, and cut off from fresh supply arriving from outside. A galaxy alone in a void is simply left to get on with things. Nothing takes its gas away, and nothing knocks it out of shape. It has time. Some of this is settled and some of it is not. That void galaxies are smaller and bluer on average is well established now across several large surveys, and the effect holds up when the samples are cut in different ways. Whether they are also poor in metals beyond what their size alone would predict is argued about. The samples are small, and small samples in astronomy have a long record of shifting once they grow. One measurement suggests there is a real difference. Another finds none at all once galaxies are compared properly at matched mass. Nobody has settled it. The voids matter for a larger reason as well. A region with almost no matter in it is the cleanest available place to watch what expansion does on its own, with very little gravity muddying the signal. That makes voids a useful test of whether our description of gravity holds at the largest scales we can reach. Their shapes turn out to be useful too. Voids ought to be round on average, since nothing in the physics prefers one direction over another. So the amount by which they appear stretched along our line of sight can be turned into a measurement of how the expansion rate has changed with time. Catalogs now list tens of thousands of them. Most are far smaller than the Great Void, and the small ones vastly outnumber the large, in the same way that small lakes outnumber great ones. Software walks through the galaxy maps the way water finds a basin, marking every low place, tracing the ridges between them, and turning what was once an oddity worth publishing on its own into an ordinary entry in a table. The empty parts have become data. There is one more thing the voids do, and it is the thing that matters next. They pull less. Emptiness exerts no force of its own, and yet the effect of a region with less matter than average is the same as a push, because everything around it is being pulled harder from every other direction. Sit between a wall and a void and the wall wins. Everything drifts wallward slowly over spans of time that make the word slowly useless. So on the largest scales, a map of where matter is heading is really a map of where matter is missing. To work out which way anything is being carried, the first thing to look for is not the nearest crowd, but the nearest empty room. So the places with nothing in them are quietly deciding which way everything else travels. None of it is standing still. The rooms and the walls and the long threads of galaxies are all in slow motion. And the motion is not random, because every galaxy is pulled by whatever mass lies nearest to it, and by whatever mass is absent nearby. That second part is the quieter half of the same mechanism, and it comes in naturally once the motion itself has been described, so it sits here until then. Neither half is complicated. Begin with the motion itself, because our own galaxy is traveling. The galaxy is not drifting slowly, and it is not being carried by the expansion alone, and its heading is nothing like random. It is leaning. Nothing about that is quick, and nothing about it arrives. Everything with mass falls towards other mass, given enough time, and the Milky Way has had a very long time. The speed is large by any standard we normally use. Something like 600 kilometers per second in a fairly settled direction. That is roughly 2 million kilometers every hour. And yet, none of it is felt here. No wind, no shudder, no sense of speed at all. The Earth carries us around the sun. The sun carries us around the center of the galaxy, and the galaxy itself is carried towards something far larger. And all three of those motions are smooth enough that the body has never had any reason to notice them. That is one of the calmer facts in astronomy. The measurement itself is a beautiful piece of work. Filling all of space is the faint glow left over from the early universe. The oldest light there is sitting now at about 2.7 Kelvin. It arrives from every direction at once, evenly, filling the whole sky. If we were sitting still with respect to that light, it would look the same on every side. Give or take the small ripples that map the early lumps of matter. It does not look the same. One half of the sky is very slightly warmer than the other, and the warm half is the half we are moving towards, because motion crowds the arriving light a little and lifts its temperature by a very small amount indeed. The pattern is smooth and it has one axis. Astronomers call it the dipole, and measuring the warm patch against the cool patch opposite it gives the speed straight out of the arithmetic, along with the heading. The sun turns out to be moving at about 370 kilometers per second relative to that ancient light. Subtract the sun's orbit around the galaxy, and subtract the slow dance our galaxy is having with its nearest large companion, and what is left over is the motion of the whole local group together, close to 630 kilometers per second. That is the number that matters most here. That figure is the motion of our entire neighborhood rather than our address inside it. The same motion can be read from the galaxies themselves, which makes a useful check. Galaxies have redshifts, and a redshift mixes two things together: the expansion of space and whatever local falling the galaxy happens to be doing. To separate them, an independent distance is needed. There are ways to get one from the brightness of certain kinds of exploding star, or from the way a spiral galaxy's rate of spin tracks the light it gives out. None of them is exact, but together they give a distance. And the distance gives an expected redshift, and the gap between what is expected and what is seen is the local motion. Do that for thousands of galaxies and a flow appears, and it is not a scatter of random wanderings. What shows up instead is a pattern with a direction, shared by nearly everything nearby. None of this motion is the expansion of space. The expansion carries everything away from everything else, patiently and in every direction at once, and it does not favor one heading over another. What is left once the expansion has been taken out is called peculiar velocity, and the word peculiar here means particular rather than strange. This is the part of the motion that gravity is responsible for. It is the falling, and it points somewhere specific. For a long time, nobody knew what lay in that direction. The heading is roughly towards the constellations of Hydra and Centaurus, low in the southern sky. In the 1980s, a group of astronomers measured the motions of hundreds of galaxies in that part of the sky and found them all leaning the same way, as though a slope ran through the whole region, and everything resting on it were sliding gently downhill. They named the bottom of the slope the Great Attractor, and the name is grander than the thing deserves. The Great Attractor is not an object. The name covers a broad concentration of mass, somewhere from 150 to 250 million light-years from here, made of several clusters of galaxies sitting close together and a great deal of matter that gives off no light at all. Tens of thousands of galaxies worth of mass, spread across a region far wider than any single cluster. And here the honesty has to come in. We have never had a clean look at it. The Great Attractor sits almost behind the plane of our own galaxy, so seeing it means looking through the thickest part of the Milky Way, through its dust and its crowded stars and its gas. Most of the visible light from behind that curtain never reaches us. That stretch of sky has a name of its own, the zone of avoidance, and it covers a band running right across the sky. Radio waves and infrared and X-rays get through it better than visible light does, and the surveys built on them have filled in a great deal, and a rich cluster named Norma has been found sitting close to the center of the pull. But the census is still partial. The census behind the disk of our own galaxy is still partial. And filling it in is ordinary slow work rather than a mystery. Radio and infrared surveys have been steadily adding to it for 30 years, and the picture gets a little more complete each decade. The direction is solid, the speed is solid, and the exact bookkeeping of which, mass, is doing how much of the pulling is not settled at all. Part of the reason it is not settled lies further out. Beyond the Great Attractor, in very nearly the same direction, sits the largest gathering of galaxies anywhere within reach of our surveys. The astronomers who mapped it called it the Shapley concentration. It lies around 650 million light-years away, and it holds far more mass than the Great Attractor does, and it would dominate the local pull outright if distance did not count against it. Distance weakens gravity quickly, so the real question is how much of our motion belongs to the nearer mass and how much to the heavier mass behind it, and different measurements give different answers. Some studies hand most of the pull to Shapley, some divide it roughly in half, and some argue that the sum of everything within a few hundred million light-years matters far more than any one named landmark does. This particular question is genuinely unresolved. Nor is it the kind of dispute that a single clever observation will close, because settling it needs better distances to thousands of faint galaxies scattered across an obscured part of the sky. That work is slow, and it is being done a little at a time. There is a related open question, which is where the flow stops mattering. In principle, at a great enough distance, the pulls from all directions balance out and the flow settles towards nothing. Some surveys find that it settles at around 300 million light-years. And some find that a broad drift carries on further out than the standard picture predicts. Nobody has settled that question yet, and it is being worked on. So the picture is a slope rather than a single destination. We are on the slope. There is one more piece to it, and it is the elegant one. Look towards the part of the sky we are moving away from, the region behind us, and there is remarkably little there. There is no wall there and no barrier, just a large region holding fewer galaxies than a region that size ought to hold. In 2017, a group led by Yehuda Hoffman mapped the flow of galaxies around us, gave that thin region a name, the dipole repeller, and argued that it accounts for roughly as much of our motion as the crowded side does. The name invites a misunderstanding, so it is worth going slowly here. Emptiness does not push. It has no force of its own to exert. The effect is real all the same, and the reason is simple once it is set out in order. Gravity pulls from every side at once. On any galaxy, the mass ahead pulls it forward, and the mass behind pulls it back, and the mass to either side pulls it sideways, and what actually happens is the sum of all of those pulls together. If matter were spread perfectly evenly, every pull would be matched by an equal pull from the opposite side, and nothing would move anywhere. Matter is not spread anything like evenly. So on one side of us there is more mass than average, and it pulls a little harder than average. On the other side there is less mass than average, so the pull from that side is weaker than it would otherwise be. The shortfall does not cancel the pull from the crowded side. What remains is a steady motion away from the thin region and towards the thick one. That is the whole mechanism. An underdense region behaves as though it were pushing, not because it does anything, but because it fails to hold on. The absence is behaving exactly like a presence. The arithmetic comes out the same either way, and when the flow around us is drawn as arrows on a map, every arrow points away from the empty side and towards the crowded side, so the empty side looks for all the world like a source. That is a neat piece of accounting. It also means the voids are not passive scenery, because the rooms with nothing in them are shaping the traffic, quietly, by not holding anything back. Here is something to hold on to, for scale. Set a coin flat on the table. If that coin were the Milky Way, edge to edge, the Great Attractor would lie about 40 meters away, outside the house and across the road. The Shapley concentration would be 3 times further again. Between the coin and the far end of that road there is almost nothing. A few specks of dust spaced out by meters. That is the neighborhood, and the coin is drifting slowly towards the far end of the road, which brings us to the largest thing we can reasonably call home. If the flow lines are followed instead of the light, a different kind of map appears. Instead of asking which galaxies sit close together, ask which galaxies are drifting the same way. Trace every flow line back and find where the basins divide, the way a hydrologist works out which raindrops end up in which river. In 2014, a team led by Brent Tully did that with the measured motions of about 80000 galaxies, and found that our own flow lines all belong to a single basin called Lani Akia, a Hawaiian name meaning immeasurable heaven. The basin is roughly 520 million light-years across. It holds something like 100,000 galaxies, and the Milky Way sits well out towards one edge of it rather than anywhere near the middle. The whole basin drains in the direction of the Great Attractor, and it is the largest structure anyone has ever put our address inside. And it may not be a structure at all. That needs saying plainly, because it usually gets left out. The basin is not defined by being held together. A galaxy cluster is bound, which means its members are gravitationally tied to one another and will stay together while the universe expands around them. It is not bound. It is defined by a pattern of motion at one moment in time, and expansion will eventually carry its outer parts away from each other. The basin will not survive as a unit. Some astronomers therefore think the name lends a false solidity to what is really just a flow field. Others point out that the boundary depends on which survey of velocities is used, and that the basin changes shape and size when the data change. Whether the basin counts as one thing is an open argument, and it is not a settled fact, so it should not be repeated as one. What is not in dispute is the flow. The galaxies around us really are moving together in a broad and orderly drift at hundreds of kilometers per second in the direction of a mass we can only partly see. The drift is gentle, whatever the numbers look like written down. At 600 kilometers per second, crossing the width of the basin would take more than 200 billion years, and the universe is not yet 14 billion years old. Nothing here happens in a hurry. The falling is real and measurable, and it will never arrive, because beyond a certain scale the expansion widens the gaps faster than the falling can close them. The motion is a lean rather than a plunge, a long, slow leaning towards the thicker part of the sky and away from the thin part behind us. It is the thin part that is worth holding on to. The same accounting that explains our motion also says something about the place we occupy. If a void behind us can move an entire group of galaxies, then the emptiness nearby is not a detail of the scenery. It is part of the local arrangement, measurable in the same units as the mass. The nearest of those thin regions is not far away at all. It begins close to the coin. The push has a source, and it sits closer to home than the pull does. Very close, in fact, closer than almost anything else in this story. Just past the edge of our own small group of galaxies, out in the direction of Hercules, the galaxy counts begin to thin and then keep thinning. The region they thin into is wide enough to have earned a name of its own. Astronomers call it the local void. The name is plain, and the name is accurate. It was mapped in the 1980s when Brent Tully and Richard Fisher were putting together one of the first careful three-dimensional atlases of the nearby universe, and noticed a broad swath of sky where the nearby galaxies simply stopped appearing in their lists. Nothing at those distances. Then galaxies again, much further out, past the far wall of it. The near edge begins only a few million light years past the outskirts of our own group. That is remarkably close. On the scale of the observable universe, a few million light years is a step across a porch, and the emptiness starts almost at the door. The far side is harder to pin down, partly because the disk of the Milky Way lies across part of the view and hides whatever sits behind it, and partly because the edge of an empty region is never a wall, but a slow return to ordinary density. Current estimates make it something like 150 million light years across. Possibly a good deal more than that, though the far edge is uncertain. Inside that volume, there are galaxies, but there are not many of them. A few dozen small, faint systems have been found, where average cosmic density would put many hundreds of them, and they sit widely separated from each other. Most are modest things, dwarf galaxies still holding a great deal of gas and turning it into stars at an unhurried pace. Nothing out there has ever hurried them along. That is the character of an empty place, where little arrives and little collides. Galaxies and voids often look younger than their age, because the events that age a galaxy are mostly encounters with other galaxies, and out there, the encounters never come. Star formation runs on quietly for billions of years, with nothing arriving to interrupt it. The local void matters to us for a practical reason as well as a scenic one. Gravity gathers matter toward matter, and where the matter is missing, the gathering is missing too. Our group is therefore easing away from the empty side of the sky while it falls toward the crowded side, and those are not two separate motions, but one motion described from two directions. An underdense region does not push on anything at all. It simply fails to hold on. Nothing shoves, and something quietly lets go. The measured drift is in the region of 260 kilometers per second away from the void, which is gentle by the standards of cosmic motion, but perfectly detectable. It has been measured more than once, and it points the same way each time, which is the sort of agreement that turns a curiosity into a fact. So part of the reason our neighborhood travels the way it does is not a distant mass at all. The local void is a nearby absence, a hole beside us, and we are sliding slowly down its outer slope. That much is settled, and it has been settled for decades. Matter on one side of us, and a great deal less of it on the other. The larger claim is a different matter, and it needs handling with more care than it usually gets. In 2013, 3 astronomers working in Hawaii, Ryan Keenan, Amy Barger, and Lennox Cowie, published a study of how the density of galaxies changes with distance from us, built on infrared surveys chosen because they catch galaxies of ordinary brightness rather than only the brilliant ones. Their result was strange. Out to a very great distance, the density of galaxies around us came out low, and it stayed low, and it only rose to the expected average near the far edge of their catalogs. Not a narrow gap in the sky, a wide, shallow shortfall, with us somewhere inside it, roughly 2 billion light-years across on their numbers, holding something in the order of 20% less matter than an average patch of the universe of the same size. The feature has been called the KBC void ever since, after the initials of the 3 of them. 2 billion light-years is not a distance anyone can hold in mind, so here is a ratio instead. Put a coin flat on a table, and let the coin stand for our galaxy, along with every galaxy it travels with. On that scale, the underdense region would be the whole room. Wall to wall and floor to ceiling, and the coin would be lying somewhere off-center on the floor. A coin, and then the room. That is the claim, and it is only a claim. Now the part that usually goes missing when this gets retold. The KBC void is one measurement, and it is genuinely disputed. Its width is disputed, its depth is disputed, and there are careful astronomers who think the whole feature is a product of how the counting was done rather than a property of the universe. The difficulties involved are not exotic ones. Counting galaxies means first deciding which objects count, and that depends on how bright a galaxy must be before a survey records it at all, which changes with distance. It depends too on how much of the faint outer light of a remote galaxy gets included in its measured total, which is a genuinely awkward job. Get those judgments slightly wrong in a consistent direction, and an ordinary universe can be made to look underdense. The tests since have not agreed with one another. Some surveys do find a local shortfall, though a smaller and shallower one than the original paper reported. Some find nothing unusual at all. Others find the density low in one direction across the sky and close to normal in another, which would make the feature a lopsided dent rather than a tidy bubble, with us at the center. The counts of distant radio sources have been used as an independent check, and they too have come out both ways. Nobody has settled it. The honest summary is that there is reasonable evidence our wider surroundings sit a little below the average density of the universe, and that the figure of 2 billion light-years is at the large end of anything anyone has claimed. The 20% depth is the most contested number in the whole business. Treat it as a measurement, not a fact. It may shrink with better data, and it may firm up instead, and either outcome would be an ordinary week in astronomy. There is a theoretical argument too, and it cuts both ways. A shortfall of a few percent across a region of that size sits comfortably inside the standard picture of how structure grew, because the early universe was very nearly smooth, and its unevenness on the largest scales is still small today. A shortfall of 20% across 2 billion light-years is a much harder fit. Not forbidden, only uncomfortable. And that discomfort is a large part of why the result gets argued over instead of absorbed. The argument found a wider audience because of a separate problem, and the two became tangled in a way that is worth pulling apart slowly. There are two ways to measure how fast the universe is expanding, and they are almost completely independent of one another. The first works outward from nearby objects whose real brightness can be worked out. Stars that pulse at a rate set by how luminous they are, and a particular sort of exploding star that reaches a similar peak every time. From those, it builds a ladder of distances, rung by rung, out into the surrounding volume. The second starts from the faint microwave glow, left over from the young universe, measures the ripples printed across it, and works out which expansion history would carry them to the sizes now seen. Both are careful and well-tested pieces of work. Both have been repeated by different teams using different instruments. They disagree with each other by something like 8%. The nearby method gives a faster present expansion than the early universe method predicts, and the disagreement has not shrunk as the measurements have got better. That is exactly why it is taken seriously, rather than blamed on sloppy work. Both numbers have been checked by rival groups with every interest in finding a mistake. The mismatch has a name: the Hubble tension, and it has no agreed explanation. This is where the void walked into the room. If our surroundings really are slightly emptier than average, then the space nearby is being held back a little less firmly by gravity, and everything around us would be separating marginally faster than the universe as a whole is separating. A local measurement would then read high. The early universe measurement, which describes the whole thing at once, would not. Some researchers asked whether that could be the answer, and a handful have argued that a deep enough local shortfall might account for a fair share of the gap. It is a tidy idea. It is also probably wrong, and most of the work done since says so. Most of the analyses that have tested it find the effect far too small to matter, on the order of 1% or less, rather than the 8% that needs explaining. Several also find that a dip deep enough to do the job would leave other marks on the sky that are simply not there. There is a second problem with it. The nearby distance ladder already reaches well past the region in question, and a measurement averaged over a volume much larger than the dip should barely register the dip at all. So the fair statement is a modest one, and modest statements are the ones that survive. Living in a slightly underdense region probably does shift a local measurement of the expansion rate by a small amount. That amount is almost certainly nowhere near enough to explain the tension, and the tension itself remains wide open. An interesting question then, and not a solved one. And it is worth resisting the neater version that sometimes gets told, the one where we live in a void, and that is why the universe looks the way it does. That sentence carries far more weight than the evidence will bear. What the evidence carries is quieter than that. Something more like this: our galaxy belongs to a small group of galaxies. That group sits at the edge of a well-mapped empty region which begins a few million light-years away and runs on for perhaps 150 million light-years. Beyond that, out to some distance still argued about, our wider surroundings appear to run a little below the average density of the universe. How far and how far below are open questions. That is the whole of the finding. That is not a distinction, and it is not a misfortune. Underdense regions of this kind are not unusual. They are most of the volume of the universe. If matter is gathered onto sheets and threads and the rooms between them make up the bulk of the space, then the ordinary address for a galaxy is somewhere out on the long, slow way in from a room, which is roughly where this one is. Out on the long, slow way in from a room, leaning gently towards the thicker part of the sky, and in no hurry about the journey at all. Slightly below average is a very common place to live. Most galaxies in the universe live somewhere much like it, and there is something to be said for it. A quiet neighborhood is a stable one. The sun has been round the galaxy 20 times or so without a close encounter that changed anything, and the Earth has kept its orbit for 4.5 billion years. Both of those facts owe a debt to the sheer quantity of nothing standing between here and everything else. Crowded places are eventful. In the dense middle of a galaxy cluster, gas gets drawn out of galaxies as they fall through, star formation runs down, and orbits are reshuffled by close passes. Here, everything is kept roughly the shape it started with. None of that has happened here. Nothing has ever come close enough to do it. Our group has been left to itself, and it shows in how orderly everything is. The same emptiness that makes the night sky look so nearly bare is the emptiness that has left this small system undisturbed for long enough that something in it could grow complicated and lie still in the dark and wonder about the arrangement. That is not a small return on an empty address. The dark overhead is part of the same bargain. Space between things is what lets light travel a long way without being interrupted, arriving thin and old and still carrying the shape of wherever it started. Light needs room, and room is what there is. Fill the gaps, and the view would close. Keep them, and there is a view. So the quiet here is not a reward, and it is not an accident of luck. It is the ordinary condition of most of the universe, and we happen to occupy a fairly ordinary part of it, a little thinner than the mean, with a well-studied hollow beside us, and a wide soft dip around us that people are still politely arguing about. A calm address, in a mostly calm place. And it is growing calmer. Nothing in that arrangement is holding still. The whole pattern of filaments and sheets and quiet interiors is being carried outward, gently and with no sense of movement at all, because the space between the structures keeps growing, while the structures themselves stay about the same size. You will not feel any of that. There's nothing in it to feel, and nothing in the room around you responds to it in any way. Expansion does not pull on your body, or on the bed you are lying in, or on the ground under the building, and it does not stretch the Earth, or the path the Earth follows, or the galaxy the sun belongs to. All of those things are held together already. Gravity inside a bound thing beats the outward drift without effort, so the thing simply keeps the size it always had. The drift shows up only in the distance between things that are not holding on to one another. Bound stays bound. What grows is the space in between, and it grows everywhere at once, in every direction, by the same small fraction each year. So the wide interiors we have walked through are getting wider, and the walls around them are thinning as their galaxies spread further apart, and the whole arrangement becomes a slightly looser copy of itself with every passing million years. The change is far too slow to watch. Across the entire history of our species, the sky has not shifted by anything a careful eye could catch. The drift is measured in the light of galaxies hundreds of millions of light years off, not in anything moving in front of us. The yearly fraction is so small that a galaxy has to be enormously far away before the effect adds up to anything a telescope can see. This is a trend and not an event. There is nothing in it to brace for. Close to home, none of it applies. Our galaxy sits inside a small bound group, the Milky Way and Andromeda, and a few dozen smaller companions, and all of them are held to each other firmly enough that the outward drift never wins, however much room opens up in the space beyond them. They will stay together. Gravity settled that question long ago, and it settled it in our favor, well before there was anyone here to be glad about it. In a few billion years, the two big ones will meet and merge and settle into one larger galaxy, and the stars inside them will almost all pass one another at enormous distances, because even when two galaxies run into each other, the emptiness is still what dominates. Almost nothing inside either galaxy will actually touch anything else. The sun will keep an orbit, the Earth will keep the sun, and the sky overhead will rearrange itself over a span so long that no single generation could notice a change. Someone will be lying under that sky one day, and it will look every bit as settled as this one does. That is the local picture, and it is steady. Outside the group, the story runs the other way. Every galaxy that is not bound to us is being carried away, and the further off it already sits, the faster the gap between us and it opens. The most distant ones are receding quickest of all. Over tens of billions of years, the galaxies in the deep images will recede until the space between us and them grows faster than their light can cross it. After that point, the light they send out will never arrive here at all. They do not blink out. The light already on its way keeps coming, so what is lost is their future rather than their past. Each one appears to slow and redden and dim across a stretch of time that no number really conveys, its last image thinning rather than switching off. A long fade, not a disappearance. The whole fade takes longer than every span in this story put together, and the difference between one human age and the next would be far too small to detect. That is the slowest possible way for something to go out of reach. Far enough ahead, the sky from this galaxy would be a local sky again. One island of stars overhead and a wide calm past it. It would look complete to whoever was lying under it, in the same way ours looks complete to us. The map being drawn now is a map of a view that does not last, which makes the timing worth being glad about rather than sorry about. We are here while the whole thing is still legible, with the other galaxies close enough to see, and their light still arriving, and the structure still open to being measured. That is a piece of ordinary good fortune. Whether the far future works out exactly like that depends on something nobody has explained. The outward drift is speeding up, and the name written down for the cause is dark energy, which is an honest label for a measured effect with no agreed mechanism behind it. The measurement is solid. The explanation is not. If dark energy carries on behaving as it has for the last several billion years, then the slow emptying goes on much as described. There are signs that it might not stay the same. And if the strength shifts, then the far future becomes a much more open question than the tidy version admits. That part of the story is genuinely unsettled. The teams behind those hints are careful to say the signs are not yet strong enough to settle anything, and plenty of other measurements still fit the simple picture perfectly well. Nobody has a verdict, so the far edges of the story are drawn in pencil, and the people who drew them say so plainly. None of it is urgent in any way that touches you. The nearest of these changes sits tens of billions of years ahead, several times the whole age of the universe so far, and the sun will have finished its own long life before the sky outside our group has visibly thinned. None of it moves inside a human span. The sky your grandchildren look at will be the same sky, arranged the same way with the same stars in the same places. The universe is emptying at a pace that leaves a human span completely untouched. There's no plan to make and no date to remember, but an emptying universe is not a universe losing something. The emptiness is not a shortage, and it's not a gap where something better should have been. Because nearly everything you value about being here depends on there being a great deal of nothing in the way. Think of the ground under you. It has held steady your whole life, and it held steady for billions of years before you, and the reason is that the path the Earth takes around the sun runs through space so empty that almost nothing has ever come close enough to disturb it. Orbits are stable because space is empty. In a crowded system, the paths would be bent and shortened constantly, and no planet would hold a steady distance from its star for long enough for oceans to settle or for a climate to keep roughly the same shape. The quiet is what let the Earth keep time. Every reliable thing you know rests on that. Seasons, tides, the length of a day, the fact that tomorrow will resemble today closely enough to plan for, all of it comes from a planet moving through a region with almost nothing in it. Emptiness is not the enemy of that steadiness. It is the reason the steadiness is available at all. A quiet region is the only kind of place where a long story can happen. The same thinness gave the sun room to burn quietly for billions of years without being knocked about by anything passing. Everything slow, from the cooling of a rock to the settling of an ocean, needs a long run where nothing interferes. Undisturbed time is what complicated things need, and a thin universe hands it out freely. The same is true of the darkness you are lying in. The sky is dark enough to see through only because the space between here and everything else is very nearly empty. Fill it with even a thin haze, and the view would end a short way out, and the sky would become a soft gray wall with nothing behind it. You would see fog. There would be no map beyond it, no history, no way of telling whether anything existed past the nearest handful of stars, and the whole arrangement of walls and filaments and quiet interiors would have stayed hidden behind the very stuff that made the sky look full. Instead, the sky above you is clear all the way out. You can check a little of this yourself on any clear night, well away from streetlights. The dark between the stars is not a curtain across the view, it is the opening, and light arrives through it from an enormous way off. Light crosses hundreds of millions of light years and arrives here with what it was carrying intact, which sounds like an ordinary sentence and is a remarkable thing to be true. That holds only because there was almost nothing along the way to get in the road. The gap is not the obstacle, the gap is the window. So the reason anyone could draw a map of the universe is the same reason the map has so little in it. Every measurement in this whole story came through vacuum. The distance to a galaxy, the faint temperature of the leftover glow, the shape of the filaments, the mild shortfall of our own region, all of it arrived as light that traveled undisturbed for an enormous time and then landed in a small instrument on a small planet. Nothing had to be cleared out of the way, because the road was already clear. And that clearness is not a lucky feature of our own patch. It is the ordinary condition of almost the entire volume, which means an observer anywhere at all would have the same open road to look down. The universe is set up to be seen through. Every telescope ever built was pointed into a gap and was rewarded for it. Hold the small version of it one last time. If the sun were a grain of sand resting on a table beside your bed, the next grain would sit about 7 kilometers away, somewhere across the town, with nothing at all in between. 2 grains and 7 kilometers of quiet. That ratio is not the universe failing to fill itself. It is the reason each grain can burn steadily for billions of years, undisturbed, holding its own planets in place, giving them the long, calm run that anything complicated needs. The distance is the gift. So the universe is getting emptier, slowly and evenly, and that is simply the shape of the thing rather than anything happening to anyone. The rooms widen by a fraction no living thing will ever notice, and there is nothing in it asking anything of you tonight. The rooms are widening by a fraction no living thing will ever notice. The walls are thinning across spans that make a whole lifetime look like a single held frame. None of it is a loss. You are inside a small group of galaxies that is staying together on a stable planet in a patient orbit, in a part of the universe that is calm exactly because so little of it is filled. The neighborhood is thin. It is also steady, and it will stay steady for far longer than anything you could ever need it to be. And it was steady for a very long time before you got here. That is a good place to be lying down. You can let the whole map go now and keep only the feeling of it. Everything tonight comes back to one simple shape, a few small things, very far apart, with a great deal of clear space between them, and the clear space is the reason the small things last as long as they do. That is all it is. There is nothing missing from that picture. The empty part you are sitting in is an ordinary part, a slightly thinner stretch of an already thin universe, and a place with a very good view out of it. Ours is a slightly thinner stretch of an already thin universe, and it happens to be a place with a very good view. From here, you can see out a long way. That only works because of the emptiness. So let the size of it be restful. The distances are large and they are calm, and nothing about them asks to be carried. The distances are large and they are calm. The quiet out there is the same quiet that let everything here settle into place. The distances out there are holding, and they hold at a pace that has nothing to do with the night. Everything is where it has been for a very long time, and it will be in the same place in the morning. The sky above the roof is doing what it has done for billions of years, which is almost nothing at all, very slowly and very quietly. The stars will hold their places through all of it. The empty rooms will widen a little, and you can rest inside all of it. The universe is mostly nothing at all. That is why you can see any of it. The emptiness is what makes the view possible, and the view is yours tonight.